This video contains the proof of Rolle's theorem. First of all, what is the statement of Rolle's theorem? Let f be a function that satisfies the following hypothesis. F is continuous on the closed interval AB. F is differentiable on the open interval AB. These are the given thing. We are going to prove the Rolle's theorem. What is our given? Our given is f is continuous on the closed interval, f is differentiable on the open interval, and f of a equals f of b. Then what we have to prove after the statement written after then is the thing that we have to prove. We have to prove that then there is a number c in this open interval such that the derivative at that point c is equals to 0. For proving this statement, we have three cases regarding our function. The first case is when f of x is a constant number. Let's suppose that constant is k. Then if we draw a graph at point A and at point B, the function is continuously giving you the same value k. Let's suppose this is a k value. So at f of A and at f of B, it is giving us the same value k. This is our x-axis and this is our y-axis. This is a constant number, any constant. Then we know that the constant number will give you the derivative equals to 0. And whatever point we put here, it will give us the same value 0 here. So the number c can be taken to any number in this open interval AB. So we can take any of the number from here to put in this one and we will get the same thing here. So we will get here f dash of c is equals to 0. So in case number 1, we have proved that f dash of c will be equals to 0. Now move on to the case 2. In our case 2, let's suppose that our f of x is greater than f of a. What does this means? This curve, it has a point A and it has a point B here, and let's suppose this point is f of x, and you can observe through this curve that f of x is greater than f of a. For example, this point is f of a. So you can see from the curve that f of x is greater than f of a here. Now what will happen here? Let f of x is greater than f of a for some x in this open interval AB, then f has a maximum value. Then f has a maximum value somewhere between this interval. Now we know that it is given that f of a is equals to f of b. It must attain the maximum value at a number c in the open interval AB. Then f has a local maximum at this point C, because we have said that f of x is greater than f of a. So it means that it will attain the maximum value at a number C in the open interval, this one. Then f has a local maximum at point C. And then f is differentiable at C. This implies that f dash of C will be equals to 0. Now move on to case 3. That will be opposite to the case 2. Here we have taken it the maximum one. In case 3 we will consider it as the minimum, local minimum. So in case 3, let f of x is less than f of a. For that purpose, it will have some local minimum point. For example, this is our x-axis, this is our y-axis. If we draw a curve here, f of x must be, for example, this is our point f of x. Here it has point A and it has point B here. And let's suppose this f of x is some point at somewhere at point C between this interval. Now here f of x is less than f of a for some x in this open interval AB. By the extreme value theorem, what we can say here, f has a minimum value. F has a minimum value in closed interval AB, and we know that in our theorem f of a is equals to f of b. It attains this minimum value, at a number C belonging to this open interval AB. Again, we will get here f dash of C is equals to 0. So using all these three cases, we have proved that if the above postulates of the Rolle's theorem hold, then our f dash of C will become equals to 0.